All right, so today we're going to begin a section on linear algebra. All right, linear algebra. Okay, first of all, it is a topic that has a kind of a loaded title. Yes, we are going to be dealing with things that are lines, and yes, it's algebra, but it's a different kind of algebra than you're probably used to. And algebra, okay, not that there is only one, there are many. Elementary algebra is what you've already learned how to do. Okay, you learned how to move x's around, solve for a variable, blah, 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 right? Okay. An algebra is a system of rules that act upon a set of objects in a certain way. For example, in regular algebra, elementary algebra, objects like a and b being numbers, a times b is equal to b times a. We have the commutative property, where a and b are elements of the real numbers. This is elementary algebra. This is the commutative property. In linear algebra, this doesn't work. Yeah, groans and moans and whines. But in fact, we'll be playing with this a while. But in linear algebra, what we're talking about are systems of equations. I should do this first. Now, these are not real numbers anymore, by the way, are elements of matrices. That's supposed to be an L, but my smartboard is not quite calibrated. Matrices of different sizes and shapes and fun, wonderful things. Things that go bump in the night. Wonderful. We're going to go back to systems of equations. All right? Go back to Algebra 1. All right? In Algebra 1, we saw systems that looked like AB plus, strike that, AX plus BY equaling some constant, and another equation, DX, and that's not a derivative like you think, where A, B, C, D, E, and F were all numbers, usually integers, okay, of some shape or form, okay? We did this. You've done this. You know how to do this with substitution. You know how to do this with elimination. You know that if you graph these guys, you can find the point of intersection, and that's your solution, right? There are many different ways of solving things like this, okay? But it doesn't necessarily have to be just an x and a y. You could have more variables. Why? Okay, think about this for a moment. Why do we? That's the first important piece. Why does it matter? Linear systems are easy to play with. They don't have square roots in them. They are one-to-one. We're not dealing with, they're invertible. We can play with them very simply, okay? We also can take things that aren't linear things, and we can look at them in small batches, small little regions. Like, for example, all right, let's say I have, how about the surface of the Earth? If we take this sphere, the surface of the Earth, and we zoom in small enough that the radius of the Earth is just basically infinite, I mean, like, in comparison to me, the size of my physical presence, the radius of the Earth is, it might as well be the distance to the moon, right? I mean, like, I can't look at I can't look at the center of the Earth as easily. I mean, that thing is far away from me. The sun, the moon, they're so huge that the curvature of the surface of the Earth looks flat to me. Which is why we thought the Earth was flat for God knows how long, right? Because it's just so big. So if we think about this for a second, we have something that's round. But if we zoom in close enough, it could be approximated with a flat thing, right? So linear things, which are flat, one-dimensional objects, can approximate things that are not flat if we get in really close and talk about them, all right? So, for example, if we have another case like this, and I say this is some function, and I want to talk about that point. Well, yeah, this thing's wobbling all over the place, and it's going to go off to infinity and negative infinity, left and right. But if I get in really, really, really close, and only talk about this area, Fluffy's going to hate me. Now that I'm in that close, it's getting to look more and more like a straight line. See what I mean? So systems that are weird in general can be approximated pretty well, as long as we're talking about a small enough area. So what we want to be able to often do is find a way to describe a really nutty system with a straight line, okay? And many, many things are done this way. For a real-life example would be, let's just say you are designing a car, and you need to run safety tests on that car, right? And that usually involves smashing it against something really hard or something moving really fast in the opposite direction many times. Well, if you're interested in finding out if the airbag is going to blow out from a front-end collision on the driver's side, do you really care about what happens to the trunk? No. So you're going to have a lot of data points at the front of the car and not a lot of data points in the back of the car, right? If you are trying to figure out what will affect the stock price for XYZ Incorporated, you're going to want to say, all right, well, hey, I have labor costs that are this much. I have seasonal trends at this time of the year. I have all of these things that matter a certain amount. Let's just say I have 5 different things that affect my stock price. Did I say 4 or 5? 5. I have 5 things, 5 different variables that can affect my stock price. Maybe say the sales in 5 different countries, right? Maybe that's, if I'm talking about my overall profit. If I sell in 5 different countries, I could say these are the sales in 1, 2, 3, 4, 5 different places. But wait, X1, which is the sale of things in, say, the United States, is going to be a heck of a lot more important to my bottom line than, say, the sales in Botswana, where I only have a very small presence, right? So what we have are weights. So here are my variables. And these are my weights. Just like on your report card, or on your progress report, your quizzes and tests weigh 90% of your grade, but homework only counts for 10. So even though you might have, 50 points here and 10 points here, one of them counts a heck of a lot more than the other. All right? And of course, what we do is we add them all up. Some other constant, P, profit, whatever, anything. Okay. If you look at your progress report, you'll see that on the two quizzes, the two big quizzes that you took, there were different weights. One of them says times 0.4 or something, and one of them says times point something else. Okay. Those are the weights, and the score you got are the variables. All right. So you can imagine that even on your progress report, there was a lot of different variables, and there were different weights for each one. Okay. So this is a linear system. It's not a line in the sense that you're used to, y equals mx plus b, but it's linear in that it behaves much like a string does. So let's write a definition for linear. Well, let's talk about this for just a hot second. So things that are linear, you can kind of, in a sense, go into the parentheses, okay? And I'm going to hop off for a second and go to a different slide. So copy this first, and then I'll show you that the things that you already know are nonlinear fit this, and the things that you already know are linear also fit this. Okay? And the other one is this. So if I multiply it by a scalar, okay, remember a scalar is something that just scales it up, makes it bigger. Okay, it's a constant. 3 times as many, right? Half as much. Multiplication by a constant number. It also can go right to the variable. For example, something that's linear all right, well, let's test the first one. Excuse me. Let's do this. That's distribution. That's a linear system of 2 variables. Now, let's say something that's not linear. You already know that the square root function doesn't give you a straight line. Forget about the constant even. Leave the constant out of it. This does not fly. Right? We know that. Can't play that game. And also, this doesn't fly. Right? Doesn't work that way. So the square root function is not a linear function. All right? Now, okay, so what And who cares? Well, all of your electronics work on linear systems because computers can handle linear systems very easily. A matrix, okay, you dealt with matrices in Algebra 2, right? A little bit? Tiny little bit? Nothing too exciting? A little bit in stats, maybe, for those of you who took stats? Oh, yeah, right. Well, guess what? No calculators, right? Okay. All right. A matrix is a collection of items that describes a system. They come in many shapes and forms. All right. This has two rows and 3 columns. This is a 2 by 3 matrix. Okay. It describes 6 objects. All right. Now, some of the properties of matrices. Matrices, you can distribute a constant to them. This is a 2 by 2 matrix. And this being multiplied by a scalar on the outside, this is scalar multiplication. All right, you're just multiplying by 5 or 20 or dividing by 2, you know, that kind of thing. You're pulling out a 1/2 idea, all right? Okay. Matrices can only add to each other if they're the exact same size. If they are not the exact same size, they cannot play. Okay? So, okay. And if you look at that carefully, you'll see that the elements in each position just added with their corresponding piece in the other matrix. Okay? The 3 and the 6 became the 9. The -2 and the 4 became the 2. 5, -8, 0, and 2. Okay? That's how. Think about this. This is really just shorthand. This is a way for me to not have to write a much more annoying thing to write, especially when they're bigger, something like that's, for example, the first row of this thing, okay? The A's and the A's, the B's and the B's, because remember, each of those A's and B's represents a variable. And all I've really done is written coefficients as elements of my matrix, okay? I've kind of abbreviated the addition of two equations into just saying, you know what, I know the x's are there, I know the y's are there. I know that the x's are going to go with the x's and the y's are going to go with the y's. The a's are going to add to the a's, the b's are going to add to the b's. I know that everybody's going to play nice according to all the rules we've already learned, and you know what, I'm just going to make my life easy and say, hey, look, I'm really only dealing with coefficients here. So all I'm going to do is I'm going to write down just my coefficients, and when I add my things, they're just going to add together. Okay? It's shorthand so that mathematicians can be lazy, which means you guys should all love this. All right. Okay. Now, if I have a linear system, such as, and I'm going to see if I can give myself a real working, honest-to-God example. Ooh. Something a little nicer, please. Okay. All right. This is a system of linear equations that you would probably do what to if you needed to solve it? What would you use? Elimination. Yeah. Elimination would probably be the way to go on this one, right? Because if you added these two equations, you'd wind up eliminating this whole column, right? All those y pieces would fall out, and you'd wind up with some, negative 7x equaling negative 14, and you're going to wind up with x equaling 2, right? Let's think about this. This is what you would do. You would do negative 7x plus 0y, which I'm not going to bother with, right? So let's just think about what we just did. What we just did right there was we added two rows. That's something that we are allowed to do. That is an operation that is allowed with linear systems. This is important because there's only 3 rules. And this is one of them. It may sound elementary, but guess what? This is elementary, but that does not mean that it is not challenging. Now, if I wanted to, I could get x all by itself. What could I do to get x all by itself? Divide by what? Y negative 7. It's the coefficient in front of the x, and really what you really want is 1x all by itself. Ha! That's a goal. But I don't want it to be 1x plus 1y equaling something, right? Because that doesn't help me. I really want a 1 for x, and then later on, you could do substitution, right? And then you would want to get just 1y. So this is a great thing. This is very good. And then later on down the road, your other later on goal is to get this equation. Whatever the heck A and B are, right? But in fact, A needs to be 1. We really want that. That's another wonderful thing, because that's part of our answer, right? Your answer is going to be 1x equaling something, 1y equaling something. I know you think, Ronco, what are you doing wasting my time? I know this, but guess what? I'm about to throw this into the looking glass. And when I throw this into the looking glass, you need to really understand what eat me and drink me do. Good. This is ultimately one of the goals that I really want to get to, isn't it? Because once you found that, whatever the heck B and C are, is really what you want. That's your answer, isn't it? All right. Now, I'm almost done, but we need to discuss the two new rules. We've already talked about one rule. One rule says I can add rows. Great. That's rule one. Here's another rule. I can swap rows. I can move them up and down. Yes, I am. I know I'm crazy, but that's okay. Hey, as long as the men in white coats don't find me, I'm all right. Okay, rule, or maybe I shouldn't say rule. I should say tool. I'm sorry? Why does it make a difference? It makes a difference when we don't just have two things. Maybe we have like 50 things. Maybe we have a system of equations of 1,000 variables, and we need 1,000 equations in order to solve it, right? Swapping rows makes life easier sometimes. All right. I'm excited about swapping rows too. All right, but Charlie brought up a good point. Let's go back up a second. And at this point, Marcus is like, whoa, what's going on? All right. How could I proceed from this step? What did you say? No. How do I get x all by itself from this step right here? How do I take away the coefficient? I don't want to divide. I'm not going to let you divide. I can multiply by the inverse. I can multiply by a reciprocal. I am allowed to multiply. Division's weird, because when I divide, I might be dividing by 0 sometimes, and I want to avoid that, okay? Well, later on, maybe one day I will explain to you that there are places where you are allowed to divide by 0. So, you are not allowed to divide. Oops. I have to multiply by a constant. I am allowed to multiply by a constant. I am not allowed to divide. What's that? I'm sorry? Yes, I chose -1/7 in order to simplify my system. All right. So this is a rule, a tool, a rule. So these are my three rules. What's that? Three rules in how to solve a system in matrix form. This is called row reduction. Now, what I'm going to do is I'm going to take my system and just bother with coefficients. I'm not really interested in writing x's and pluses and all that stuff. I'm lazy. Okay. So I'm going to take something that looks like, what did I say? -2, 7. And now here, actually, these were, for a second, yeah, sure. Sure. So I have a matrix of just the coefficients from this system that I wrote, or that you guys already wrote down a minute ago, right? And what we also have is a solution matrix. And I think, what were they, 10 and -24? Multiply matrices together. We're not going to worry about that right now. Instead, what we're going to play with instead is how to reduce, because I think that's a heck of a lot more fun. Yes, in a masochistic kind of way. Sadistic, yeah, absolutely. Great word, to augment. To augment means to add upon. Okay, to increase in size by adding onto it, for example. Okay, if a student is added to my roster, they have augmented my roster. The roster is now larger with the addition of an additional subject. What's that? Oh. It was a vocab word you've already seen? Good. This is the augmented matrix. Take a look for a second. Yes? No, I augmented. I didn't add, I augmented. Okay. I now have a matrix that contains all of the real numbers, in fact, they don't always have to be, all of the numbers related to my system. Okay. Now, this is where I start. This is the beginning of the problem. The goal is something that looks like this. Now, if you look at that, you'll see that that looks like, if you were to think back as to the system that it belongs, this thing actually represents. This is 1x plus 0y equals a, whatever the heck a is, it's some constant. Okay, that's part of my answer. And the other line down here, 0x plus 1y, is some constant b. This is the goal. The trick is to go from here to there using the 3 rules that I showed you a minute ago and wrote down right a moment ago. Okay? So this is the starting material, this is the finish line. When we've got here, we're done. So let's do one. Now, we've already seen the matrix that I've already showed before, and this matrix, we're going to actually solve this beast. Okay? So, the first thing that I want to do is I want to get a 1 somewhere. If I can eliminate a whole column, more power to you. I want to make some zeros. I like zeros, I like 1s. And we're going to attack the first 2 columns. Okay? Now, I have to start making judgment calls. How can I begin to chop this beast apart? I can attack this row, this column, excuse me, or I can attack this column. Which column do you think is easier to get rid of or simplify? The second one. Good. Here's the notation. Row 1 plus row 2 stores, now I have to put it somewhere, okay? Once we've added these 2 rows together, that has to go somewhere. Now, once I've done this, and I've gotten my -7 plus 0 equals -14, it's got to be put somewhere. Let's put it, and I don't really care. Not yet. Maybe later I will. Let's put it in row 2. This thing results in, now I didn't change the first row. The first row has not gone anywhere. It's still the same. Now when I add the 2 rows and replace the second row with it, I wind up with -7, 0, -14. Okay? First of all, do we all understand what the heck I just did? What I just did was I did this, what you did before. I added my 2 rows together. I added my 2 equations. And now I have this again, or back. All right? The first one didn't change. I just used it. I used it to simplify the second one. Okay? So now, I've got a 0. Hot stuff. What I really want is I really want my goal. Remember what the goal was. 1s and 0s all over the place, right? That was the trick. How do we maybe get from this equation, this system, into something a little simpler? What can you do? I could swap rows. Fine with me. Let's swap some rows. Row 1 swaps with row 2. Just change places. There are a million different ways to solve this problem, man. There is no wrong way to do it. All roads will eventually lead to Rome. All right, I'm closer now, aren't I? Remember what the goal was. 1, 0, 0, 1. I got a 0 in the right spot. Whoopee. Now what? What I really want is 1, 0, 0, 1. I want something that looks like, am I getting closer to it? What can I, yeah, say it. What constant? Not just 1/7, negative 1/7. Negative 1/7 times row 1. And I'm going to put that in place of row 1. This more complicated row 1 will become a simpler row 1 in a second. Does this make sense? All I've really done is do what you normally do, but I'm doing it in a systematic way. Yeah. Yes. All right, I'm getting closer. I've got my first row under control. Now think about the final goal. Final goal, 1001. What has to go away? What has to be destroyed? The 2 has got to go. The 2's got to become a 0. All right? I mean, I can't multiply row 2 by a number, right? We already know that if we multiply, the only way that I'm going to make that 2 into a 0 by multiplication is by multiplying by 0. I can't divide. All right? Multiplication or division isn't going to help me get that 2, negative 2 into a 0. What can I do to make that 2 into a 0? That's right, I could add 2 to it. All right, good. I could add 2 to negative 2. That's what he was thinking. And him too. And all of them. Where am I going to get a 2? The 1. I've got a 1. And I could make the 2 into a 1. I could make the 1 into a 2. Right? I could multiply 2. 2 times row 1.
Oh, and then you add.
And then I could add it to row 2. You see how that? Ah, yes, all right, yes. The men in white coats are not here yet. Good. And now, where am I going to put that new row? Into row 1 or row 2?
We need to put the arrows underneath the.
Which one?
You're drawing arrows underneath all of your commands.
Yes.
You see that?
Yes, you should. Now, does it matter where I put it? Yeah, you see, if I stored it into row 1, what would happen? I'd lose row 1, and I like row 1. Row 1 is done. I don't want to lose row 1. I want to clean up row 2, right? So I should throw it into row 2. Now, yeah, by the way, I did multiply row 1 by 2, but only temporarily. And now this becomes a 0. Can we all say yay?
Yay.
Yay. All right. Now, what happened here? It's still just 7, because I multiplied 2 against the first row, and 2 times 0 is 0. And then I added it onto the 7, and it stayed 7. What happened here? What happened to that? Yeah, I multiplied this row by 2, which made it into a 4 for just a second, right? And then I added it onto the 10, and it became a 14. Hold on. Now what am I going to do? Multiply row 2 by 1/7. And what do I do with row 2 now that I've multiplied it by 1/7? Where does it go? Onto row 2. Huh? I have to tell you where it's going. And that, my dear friends, was the goal. Does this make at all any sense whatsoever? Does anybody know what the heck I'm doing? Good. All right. Let's try one a little bit weirder. Why don't you try this on the boards? Go to the boards. As long as you're not breaking the 3 rules in the process. Okay, now, you can erase anything that's there. It's all garbage. It's all old. All right, this one maybe is a little bit weirder. Now, by the way, I should say this, that getting a 1 and or a negative 1 are just as good for me. Okay, if I can get a negative 1, that's wonderful, because a 1 and a negative 1 are only a negative sign apart. I can just multiply a row by a negative 1 and I'm happy. So which column do you want to attack first? The left or the right? I don't care. But we have to figure out a way, we have to figure out a way to make a 1 somewhere. You want to attack the 9 and the 8? Because I need to get a 1 somewhere. Or a negative 1 somewhere. I don't care. Just give me a 1. I don't care what sign it's got in front of it. Just give me a 1. What am I going to do? Huh? I don't know. I didn't hear you. The 9 and the 8. Okay. How am I going to turn a negative 9 and a negative 8 into a 1 or a negative 1? If I added them right away, I'd get a negative 17. But what could I do? I'm not really allowed to subtract, but what can I do? I can multiply somebody by negative 1, and then add them. So who am I going to multiply by a negative 1 and then add? You want to multiply the first one? Okay, let's do that. Negative 1 times, or negative 1, whatever, negative 1, row 1, plus row 2. And where am I going to put them? Do I care at this point? Should I even bother caring where I'm going to put it? I don't care. Where you want it? You want it in row 1? Fine with me. I don't really care. All of the information is still in this matrix. I haven't created any zeros yet. When I start creating zeros, then I'm going to not want to lose a 0. Zeros are happy. 1s are very happy. 1s and zeros together are just running and playing in traffic. All right, now, so if I added the 2 and stored it here, first of all, negative 9, negative 8, negative 95 is not going to change, because I didn't store anything into row 2. I only stored it into row 1, right? So, in your mind, think to yourself, take this row, multiply it by negative 1, so you wind up getting, you don't have to do this, that's what you get when you take the first row and multiply him by negative 1. And then you add those red numbers onto the row below it. You see? That's what I just described right here. That's what's going on in this little scratch work onto the side. And the result is do you see how I did that? Ooh, this one isn't as nice as we thought it was. You want to put that into the bottom? Fine with me. I'm good with that. He wants to swap rows. I don't care what you do. I can't subtract. I can't divide. I am allowed to swap a row. I am allowed to add rows, and I am allowed to multiply. I don't care how you play this game. All right. So we haven't done anything thoroughly exciting yet. But I would really like to get a 0 now that I've got a 1. Say that again? I can think of some really evil problems where you might have fractions in there. I've even done trig equations. I've done complex numbers in there. Oh, yeah. Yeah, it was right. Yeah, I know. Imagine a matrix with complex numbers. Fun. Yeah, that was on a test. That was a test question once.
And then how many people got it right?
A few. Many. All right, now I want someone to explain to me why I'm about to do this. Why am I doing that? To turn the 1, sorry, to turn the 8, the negative 8, into a 0. Because remember what the goal is. 1, 0, 0, 1. Yeah, it's 1, 0, 0, 1 with constants, right?
My answer is to prove how I got it.
Yes.
It's like someone else could have a completely different...
Totally different way of getting there and still come up with the right answer. All right, so 8 times 87, that's 56 and 64, so 607?
Yeah.
So 607 minus 95 gives me 512. Oh, no, wait, it's negative, right?
Yeah.
No, it isn't. Yeah, it's negative. Negative 13 times 8 gives me 80 and 24, so positive 104. Negative 104. Is that right? Right, okay, so, say it again? Hold on, I want to make sure I'm right. 8 times, yeah, so 8 times negative 13 gives me 80 and 24, so 104. Negative 104 minus 9, negative 113. But I don't like the fact that that's not divisible. Did I make a mistake? Yeah, I think this is where my error is. 87 times 8 is 64 and 56. So 604 Right. $706 minus 95 gives me 801. Do we all agree with that?
Yes.
Yes. I'm excited too, because guess what? How the heck am I going to get that first row under control?
Okay.
Not magic.
Magic. You can multiply by
Say it.
negative 1 over 1.
Right.
I care about that.
And that becomes yay. I'm excited too. Because 7 times 113 that's 770, 700 and, well, did I make an error? I don't think I made an error. I might have made an error. Did I make an error? I must have made a small error somewhere. Where's my error, guys?
Well, it's not.
You scroll down. Where do you get that 106?
Oh, 696. That's why I'm off by 10. Yeah, it's that adding thing, guys. So, and now it's right. Adding. It'll get you every time. Lot of choice, lot of chances of making little tiny arithmetic errors. I'm not immune. No calculators. Calculators are for the weak. It is still a 7. 7 times 113. That's 770 plus 21. 791. Now what am I going to do? One second. Yeah, I almost want to do that, but the problem is as soon as I do that, now I've got 1 over 13 in the place of the 1, which I really like. Yeah, the only problem is that I have to distribute that 13 across everybody. And then that 1 becomes 1 over 13. I don't want to get rid of the 13 I want to turn the 13 into a 1. I want to turn the 13 into what? Right. So how am I going to turn negative 13 into 0? Add 13. How the heck am I going to get 13? Multiply row 1 by 13 and then add them, right? So 7 times 13 is 91, right? 91 minus 87 is 4. And we're done. Does that make sense? And you know what we could do? You know, if you want to be sure you're right, you want to check your work, here's how we check our work. Remember what you have. You really have now x equals 7 and y equals 4. Right? 1x, no y's equals 4. no x's and one y, sorry, one x and no y's equals 7. No x's and one y equals 4. That's really what you're looking at, right? So let's plug it back into the original equation and see if it holds. So it's right. You try one. I'll give you an easy one.
See those words from you. That's the scary thing. That makes you consider.
I will leave this to you. You have a good 15 minutes to do it, more than enough. This episode of The Ronco Show has been brought to you by Row Reduction and the 3 Rules.